Today I'm just going to have a quick introduction of the NestNet neural networks. With the presentation, I'll firstly go through CNN overviews because most of these models are based on CNN, so it's a good idea for you to get an understanding of the very basic CNN, how it works. And then we're going to move on to neural architecture search, which is what we'll call NAS from this point onwards. Then we're going to move on to its extension. That's its EfficientNet, because with EfficientNet, it's based on the NAS results I got in the previous papers. So first we'll go through the CNN. Overall, convolutional layer architecture is can be very simply understood. So you have an input layer that goes into the network and extract features and then learn the features, and then at the very end you flatten everything out and then feed that through a fully connected layer that give you the softmax predictions. That's probably a very simple example of how CNN is structured. Obviously, there's more complex structures such as ResNet that's using convolutional layers, but this is just giving you an overall idea of how it works. In terms of kernels, how they're extracting the features, this is basically what you can do. You have a 3x3 kernel here with all the weights as well as all the image inputs. All you do is you just do a dot product everything, and then that will give you the feature maps. This feature map, the stride in this sense is how much it moves. For example, the example here shown is stride 1, so it's moving 1 by 1 each squares. If you have stride 2, it will move 2 by 2. And in terms of padding, you're just adding on an extra input layer on top of the image, so you can learn more specifically on the edges. This is the very basic of what CNN does and how the CNN feature extraction works. Now we move on to the core of our presentation, the neural architecture search. The reason why neural architecture search was developed because we, as humans, we kind of plateaued in terms of designing architectures. We have AlexNets, we have all the ResNets, but since then, there's no real innovation in designing any new architectural network that will outperform the previous ones. So Google came up with the idea that try to use computer to search for architecture instead of humanly manually designing for one. So this is the motivation for why they want to use architecture search. In the paper, the overall structure is actually predefined. So they will have two cells, normal cells and reduction cells. With normal cells, the feature maps that you have actually returns the same feature map. So for example, if you have an input of 32 by 32, you have the output by 32 times 32. So that's for the normal cell. With reduction, it reduces the output size by a factor of 2. So for example, it will go from 32 to 16. That's their overall structure. With n number of stacked cells, that's actually predefined as well. So overall structure is all already predefined in the paper, and all it is training different weights for each layer. That's it. The reason why they want to search for architecture is not the overall architecture that they're interested in. It's more of the in each cells, how you can actually have a very efficient cell towards each specific tasks. That's what their main goal is going at. And you have two different types of cells, obviously, and that just gives you a bit of variety. So your cell is not very what's called singular, so you can perform multiple tasks by having two different types of cells. So you have more in terms of like activation functions. You can have different activation functions if you desire in any of the cells. And then we'll go on to the cell search space. So in their paper, for each cells, you can use the below operations. So you can either have identity, which doesn't change anything, or you can have 1 to 7 and 7 to 1 convolution, 3 times 3 average pooling, and all the others. Basically, the machine can can select any one of these for any given operations, and then the operation can be done after concatenating everything together. So this just a quick overview of RNN. The RNN, what you do is you have a hidden layer stage in each stage, and then you concatenate everything here through a gateway of 10H, and then you basically pass it on each loop as a sequence. So for them to actually search for architecture, they use what we call RNN controller. So the first step is that they use a hidden state from HI and HI minus one. That's the first two here. So basically you see the search space that was shown before. The RNN controller select one of the hidden states. So it selects any of the operations that can be done. And then they also select another one. That's their basically first steps. So you select two here, and then you concatenate together. And then the next step onto it is select a second operation onto the first hidden layer that you have chosen. And then after that, you have another little cell in RNN that selects the third operations for the second hidden state. And then lastly, you select an operation to concatenate together. If you look on the right-hand side, it's probably more clear. The gray one on the bottom is step 1 and 2. So you select two hidden layers first. And then this is step 3 and 4. So you select two operations for these two hidden layers. And then this is the last step where you select operation for concatenating the layers together and give you a new output hidden layer. And then you basically going through this over and over again, repeating this B times to give you the desired cell architecture that you want. So for how it works, so obviously you have the RNN controller in here. They will sample architecture with randomized, and then they train the child network with architecture A, so that's the randomized one, and they get a probability. And then they're going through it again, because you're going to repeat it for B times. So you're going through it again and again until they reach a point where, well, at least for them, they didn't have a controller that automatically stops. So basically, they have what they did is they stop at, I think, 1,000 searches, and then they stop there, and then basically just concatenate all the child network and then train on the child network. And how they train on the child network is basically through reinforcement learning. The gradient they have is the joint probability of all the child network altogether. And what they try to do is maximum Q. So you use gradient descent, obviously, for helping you to use to train a reinforcement learning algorithm. And that gradient descent is the gradient they have is actually the joint probability of all the child networks altogether. That will give you, that's how you train your RNN. Once you train your RNN, it's very basic for you just to use the RNN and basically run the prediction again, and that will give you your cell structure. I think this is spelled 10B. So why is it 10B? Because B is number of times you're going to repeat the predictions. If you look at here, it's repeated B times for each repetitions. You've got 5 selections to make. That's why it's 5B at the start. And also you've got normal cell and reduction cells. So that's why it's 10B, so 2 times 5B. That's why we get 10Bs of predictions. And then you just softmax them to give you, to train your RNN through reinforcement learning. And that's basically, if you want to get really deep into the mathematicals, that's the gradient that they used. So here is the activation of each child network given the parameters, and that's the accuracy basically as on the holdout data sets they achieved. All we want to do is do a gradient descent on that, and this is just basically, if you have that, that's the whole on the whole data set. And this is basically you're doing a mini batch. That's why it's RK instead of R. And then k equal to 1 to the m, and m is number of mini batches you want to do. And this is example of normal cell and reduction cell. As we can see, that's a hidden layer here. It will go pass it onto a separable 5 times 5 convolutional layers, And then this actually going from previous states into 3x3 convolutional layers, and then concatenate them together, and then concatenation at the very end. And then this is one iteration of their layers. So you have one hidden state going to the next hidden state. This is just one hidden state what they selected for the cells. Obviously, you can have. I'm not sure how many they've had with their hidden states. They didn't state that, but they said they did have 100 different hidden states for the initial search. But at the end result, they didn't state how many they had at the very end. And then this is the reduction cells. It looks a little bit different. What happened is the only difference between the reduction cell and the normal cell is reduction would actually has to reduce the size of the input. So we will have an input of 32 and then an output of 16. What they found is that with the cells, they really like separable convolutional layers. So they want it to be separately trained. They don't want to have any residuals from the previous layers. And what they also found is that the RNN controller really likes skip layers. So it's sort of like ResNet, where you're skipping through some of the unused or unnecessary layers. That's what they found in the paper. But the thing is, with their paper, they actually didn't do the skip mechanism. They only did the normal search and that's it. With the skip layer mechanism, they actually did in one of the presentations on their paper later during a global conference. So this is the results that they've obtained. So the top one is for Sapphire 10, I think, and the bottom one is for ImageNet. Obviously, you can see that compared to DenseNet or other, this basically what they found is the most popular ones that on Sapphire 10. You have better, well, at least equivalent results with less parameters. And then in terms of the NAS, in terms of the ImageNet though, you found significantly better in terms of results, and you actually reduce a lot of parameters that in turn give you more efficient. So if you compare, let's see, the Inception V2, that's a very popular one that's being used currently. They have 11.2 million parameters, given the NestNet has 10.9 million ones, and these actually have better top one accuracies and then equivalent top 5 accuracies. The only thing is, even with the improved efficiencies, they still use 500 GPUs to train for 4 days. So unless you have the resources to, you can actually just use their pre-trained network and then just adjust the weights and then adjust the prediction layer so it suits to your data. This is a comparison between the number of parameters as well as number of the accuracies they've got. You can also see that this is the baseline models compared to all the other ones that we have on ImageNet. Both of them are based on ImageNet. This is number of parameters. This is the multi-add operations. This is basically how many operations you need to done for you to train the model. This is how many parameters you need to be tuning for your model to work. We can see that the NestNet actually outperform most of the model by a large amount. If you have the parameters set as 20 million maximum, the smallest NestNet can outperform most of the humanly designed architectures. So then this is some novel research after the initial paper has released. So first thing they did is instead of searching for the cells, they also search for the architecture and how they're actually going to implement skip layers in their architecture. So what happened is you're still using RNN controller. So this is their normal cell searching, but they've adding an extra layer, extra hidden state here instead. That's actually just for layers. So in each layer, you have your own cells. That's how you search the layer, like on the top one. top 5 would just be the same original one as we saw previously. That's basically what top 5 hidden state is doing. It's selecting the hidden state for the cell is the actual normal cells and reduction cells. And then the bottom 5 is basically try to calculate, can we skip these layers, or are they really useful? They basically as a background checking sort of thing. And then this gives you the anchor points. Then they add in the anchor points. Anchor points will decide whether or not to skip this whole layer or not. So that way you can be trained faster and have better efficiency. And then after training, basically we've got this sort of this structure, but they haven't published paper on that just yet. They only did a presentation, I think, late last year in December. But with the presentation, they are more focused on what they recently published, which is the evolution algorithm to search for methods. So with evolution, they use what they call NEAT. That is developed actually quite long time ago, in 2002, which is approach to for evolving neural networks using genetic algorithm. So Google later basically developed some other nets as well, neural networks using NEAT. But their algorithm, they named it as aging algorithm. The aging algorithm is fairly intuitive. So you have the fittest survives, and then the oldest die. So for example, you have 100% in the population. The next child is obviously going to be somewhat better performed than the population. And then you remove the oldest in the population that's being added at the front. So if you think your population as a list, you will have the newest additions adding onto the end of your list, and you're removing everything that's from the beginning of your list. So if you add 1, you will remove 1 from the beginning of your list. And then that way you keep your population number in your population constant with each generation. And then in terms of mutations, how you actually develop your next child, they got 2 main different type of mutation. The first is hidden state mutations. Essentially what it does is it rewires the connection between each hidden layer. So for example, here you have the state 3, hidden state 3 originally going to the 7x7 and 3x3 average pooling. And then you remove this connection entirely and rewire it to the 4th hidden state. So that's what you do, what they mean by hidden state. So you don't change the operations at all. All you do is you change the order that hidden states go into the operations. And you can only change 1 hidden state in each mutations. So you can obviously change more, but it just sometimes they found it that if you change 1 or 2 or more, the accuracy goes all over the place. They feel like the choosing 1 is more stable. That's what they state in their findings in their paper. And then you got second type of operation mutations, which these mutations, instead of actually changing the wiring of the hidden state, you change the actual operations. So for example, you can change your operations to none, or you can change your operation to a 3x3 convolutional layer or max pool, depending on what you do, what you're being replaced with. And that's all random chosen. And the third mutation is actually identity mutations. So they don't do anything. You just copy the parents and then pass it on to the next one as a child. But that rarely happens in the paper. And it's not even talked about much in the paper as well. So I don't think that's very important. Obviously, you can have that, but sometimes they say it reduces efficiency. Then this is the algorithm. I'll actually go through a code with it later after we finish the initial presentation. But I'll just go through the algorithm for now. So first of all, you have the population as an empty key, and then you have your history as an empty key. Then you have your population set as a number. So this is the number of models that you have in your population. If you set up 10, you will have 10, always have 10 in your population. So then you do a random search in your architecture. So that just very randomized initializing your one architecture that you can have. and then you will train and evaluate that. You will add your model to the right of your population, and then add a model to your history. And history is basically how many evolution you want to do. So if you have history 100, it will generate 100. Sorry, if you have history as 100, you will generate 90. Yes, you will generate 90 generations, because what happens is you have population of 10. Initially, you will have 10 in your history, and then after you have your after your initial population is added to the history, the addition ones, that's when your evolution comes in. So say, for example, you have 10 in your population, you have 100 in your history, then the difference of 90, that's how many times your actual algorithm gonna evolve your model. And in this while loop, basically that's the evolutions. So at the very start, you have your sampling. The sampling is just random sampling of candidates. And for example, let's just say 5. So you would add 5 random models into your sample sets. And then you choose the highest accuracy of the model in your sample set as your parent. And then you do the mutate, basically what we talked about before, either operation mutation or hidden layer mutation. So you either rewires your hidden states, or you just replacing one, or even add one completely new hidden state, new operation to it. And then you will evaluate your child accuracy, and then you add your child onto your population to the right, and as well as your history. And this is way different from the original what we call genetic algorithm. They remove the oldest from the population. So because when you're adding all your models to the population, you're adding to the right. So the left of population is the oldest. So each time they're only doing one addition into the population, so remove one from the population from the very left. That just means that you will keep the number of the model in your population constant. And by doing that, it actually improves accuracy, improves efficiency. And then after you've done desired number of cycles, you just return the highest model in the history. The history keeps all of your evolution steps as well as the initial randomized one. And obviously, hopefully the last couple ones will be the highest, but regardless, this will take the highest accuracy model in your whole history batch. And then improvements in terms of, we have the random, this is a random search. So basically just searching it by randomizing. And this is by reinforcement learning, where the RNN model was based on. And this is by evolution. So you can see evolution actually picks, have good accuracy at very first and very quickly, and then plateau sort of converge with the reinforcement learning. So that's why I think for us, especially if we don't have the same computing power as Google have, the evolutional algorithm can be beneficial, because our training time is probably not going to be at this end of the scale. We are more probably aiming towards this end of the scale. And that's where the evolution algorithm can actually picks up, and can actually produce positive results. And you can also see this here. This is in terms of flops. Flops basically is how many floating points floating points operation per second. So that's how many floating points you are doing. So how many calculation basically you are doing in terms of getting a model fitted. You can see the evolution is basically outperforming all the reinforcement by quite a margin in terms of the number of calculation required. So that's one of the improvements they did. And this is quite recent. I think the paper is published 2019, end of 2019. But yeah, that's their final structure pretty well, and their final results with the comparison to their NestNet. So NestNet A is the reinforcement learning RNN model they have previously, and you can see the Amoeba net. That's their what's called the aging evolution search algorithm. And the performance is actually quite similar, not if not better. But we can see that there's a reduction in terms of the operations as well as the parameters. And this the one here, the extremely small one where you see the parameter is only 469 million. Oh, sorry, the extremely big one. That's when they did this on their Google in-house data sets with 300 million images. And then they did a search on that, and that's the results they're getting. So they're just showing you that even with increasing data to, absurd amount of computation power, the improvements on their accuracy is not as much. So that's just confirming the plateau of their algorithm. So basically you have really huge hike at the start and then it just flattens out at the end. This is just confirming that curve basically. And then we move on. That's all for the architectural search. Should I take some question for that first before I move on to EfficientNet?
Yeah, if there's any question from Kira.
Yeah.
Yeah, I just want to inquire, so the iron controller, basically that sort of predicts, so that sort of,
I'm a little bit confused the difference between the genetic. This sounds very like the evolutionary algorithm. Sounds very much similar to the genetic algorithm, isn't it?
Yes.
So what's the difference? You did point that out, but probably I missed it.
Yes, no worries. So the difference is actually, so if you look at the actual algorithm, from the starting to the here to where they add the child to history, that's the genetic algorithm. What they did differently is removing the oldest from their population. So this step at the very end and then discarded that.
The oldest, but shouldn't that be based on the performance? The oldest would be the good one.
The thing is because each mutation they're selecting,
they're meant to be better.
They're meant to be better. Yeah. Right. So that's why they think, because in the genetic algorithm you're not sampling, you don't have sampling. You just pick in the genetic algorithm here, basically you have the sample and then you sample them and then you have the parent as the highest accuracy model. Because that's the higher accuracy model in the sample. But in the genetic actual NEAT algorithm, you don't have the highest accuracy model. You're just randomly selecting parents and then mutate on top of that. So you keep all of your data. You don't reduce your size of population. Your population just kept on growing with NEAT. But then that's a lot of sampling, and that's a lot of try to get the highest training. So what they did is, instead of doing that, they have the highest model accuracy model. Yeah, that sounds better.
That could be used with any combination of other type of models.
Yeah, that's right.
Machine learning.
Yeah,
that kind of thing.
So that's why they use aging evolution algorithm instead of the NEAT, because I think they try NEAT and it's just not realistic to train on that. It just takes way too long, and they don't have the resources to. So they came up with this idea and try to shortcutting the evolution. Yeah.
Yeah, that sounds good.
So we'll move on to EfficientNet. Yeah. So EfficientNet is so as we saying before with this structure. Sorry, let me just go back. With the overall structure of NAS, NestNet, the overall structure is set predetermined by humans. So this overall structure is not changing. We're only searching for the cells in terms of NestNet. So what they happen is they were thinking, okay, so how can we actually have better overall structure? That's when they came up with EfficientNet. So the job of EfficientNet is try to search for overall structure.
So that NAS paper was before that EfficientNet paper. Okay.
Yes, and then they use the results of the NestNet and then put that onto the EfficientNet. Yes.
Right.
Yeah. So they're taking the NestNet one step further. So obviously this is the convolutional chains. You usually have 3 dimensions. You have your width, depth, and then resolution. If you look at this, that's how the image. This is the resolution basically. The image width, image height, and the image depth give you the resolution of your picture. The depths can be think of as channels. So you have, for example, this picture would be a colored picture because you have 3 channels input, and then obviously the height and the width is depending on how well, how high the resolution of your picture is. And in terms of depth, in terms of depth referring to how deep your model is. So basically how many layers are there in your model? That's the definition of depth. Wide means how many neurons are there, or how many convolutional or concatenating layers you have. Sorry, concatenating cells you have in each layer. That's the width of your model. And then the resolution here is basically because with higher resolution, you definitely require higher, you have a bigger feature maps, just because you have more information to extract from the same kernels. For example, if you have a 3x3 kernel, try to extract from a 32x32 image, it's not going to be the same. The feature map is going to be smaller if you're extracting from a bigger image. That's basically what they mean by higher resolution. So with how they deal with resolution is that if you have a higher resolution, for example, 4K image, and then they found out that it's not necessary to go through the whole image, they would reshape the image down by vectorizing some of the parts of the image. So they have a little convolutional layer that's trained specifically just for reducing its size down. So you have your first layer, for example.
Okay, so they don't just shrink it to the small.
No. They're using a CNN to shrink it down to the right size. But that layer is actually trained separately from this. So that they avoid shrinking it down and losing some of the important features, basically. And then this is the model that they got from the NestNet. They're using the reinforcement learning with RNN. They're not using the genetic algorithm yet, because by the time when they did this paper, the genetic algorithm wasn't discovered yet. This is the basic model they have. So you have the 3x3 convolutional layer. I assume, well, from my understanding, that is just for shrinking the resolution. So you have that basically picking up all the efficiency, and then you have your actual model from that point onwards. So they have the inverse residual block. If you think of a residual block, it's usually going from bigger size then to smaller size and then coming back to a bigger size. But this the residual block they searched and found is actually going from a narrow size. So in terms of the width of the number of features. So you have a narrow feature size and to a bigger size, and then back down to a narrower feature size again. And then obviously you have your skip layer in between. That's why it's residual. So this is the structure they have for their baseline model, obtained by using the neural architecture search. So they're using this. So this, I'll go through their optimization, how they did that. So for example, this F is number of layers being repeated L times. So X is your input, obviously that's height, width, and your channels. And this is the overall architecture that you have, basically. And then what the main goal is try to get the highest accuracy with a given architecture width, given architecture depth, and as given architecture resolution. And then they also have their target memory and target flops. That's just limiting the resources that they can use, basically. So they don't want to, for example, to use extreme amount of resources just to search for the best best scaling numbers. And with depths, they have d equal to alpha to the sigma. And then you have beta, and then resolution you have gamma. And then this is all being limited as well. All they did here is just making sure that it converge, basically. Otherwise, if you have no limitations, what happens is it might just search towards one direction purely. So the computer will have depth as 1, so basically not changing it, and the resolution is 1, and then search a hugely really wide wide network instead of actually going all 3 directions, because it's more efficient to use all 3 dimensions instead of just 1 dimension. But sometimes they can stuck in a loop where they're just going off onto one direction. That's why they have these constraints. And then for how they actually search their masses, it's fairly simple. So you have your power set to 1 at the very start, and then you basically do a grid search for equation 2. So basically you have grid search of that, try to find the best accuracy, just trial and error through a lot of numbers basically. And then they found that our ImageNet, the alpha is 1.2, the beta is 1.1, and the gamma is 1.15. And then on step 2, because you've already obtained this from step 1, you keep them as constant, and now you try to scale your power. So you scale that using basically this constraint, and then in the paper they are able to find the B1 model to B7 through scaling. So B1 and B to B7, they have the same base, so same gamma, same beta, and same alpha, but they have different scaling factors at the top. So this basically is how they perform compared to a pure NestNet. That's NestNet A, that's basically their base. And then that's after the initial scaling with the beta and everything fixed as 1. They already have obtained a 2% increase just by scaling it properly. And then that's scaling even further through powers. And then obviously that's efficient at B6. And this flops basically means how many calculations you need to actually obtain, to finish calculating the image. The further to the right, the more resource intensive it is. So you can see that actually with the NestNet, if you think of NestNet as the baseline, from baseline to actually improve up to 82%, that's an almost 10% jump in their accuracy without needing much resources. And that's why they think this model is actually efficient. That's why they call it efficient net. And yeah, that's it from me. Is there any questions?
Okay, any question, guys?
No, not from my side, but that's really good, John. Like, thank you for the presentation.
Right, so this is the working code for the aging algorithm. I did a very simple one on Software 10 with a sequential convolutional layer, just to give you the idea of how the actual aging algorithm works. So this is your random architecture. For me, it's CNN layer. So I have very simple max pool CNN, it's convolutional layer with the 3x3 and then average pooling. That's all the search building blocks I'm giving it. And they can search through that. And for the initial model, I've asked it to search through this space for 3 times. And then just whichever it will have, then that will be my baseline model. And this is basically, I'm just testing out how the baseline model works. So the base model will just, random search. This is the number of class you wanted. At the top, I've calculated the number of class from here, from the data sets. So after inputting the number of class, with batch size of 256 and output of just 2, because I'm just testing whether or not it works, it will output a structure like this. So a convolutional layer at the very start, and then it went into average pool, and then it went into another convolutional layer before it flattened everything, tens, and then a dropout layer, and then onto prediction layers. That's the very first randomized model is searched for. And after that, what you want to do is you want to have your model a train evaluation function. So this basically just grab the model, grab number of classes, and just train and give you the trained model and as well as the accuracy. That's a very standard the Keras training section. And then this is the operation mutations. So that's how I do my mutations. So at first I get number of all the layers that in the model, because the last 4 layers is my prediction layer, so it wouldn't change no matter what. So that's not being searched. But all the other layers that's being searched and being mutated. So I will first get all the list of layers from there, and then I will random select a layer a single cell in the sequential model, and then I will start writing my new model. So in the new model, it will have if the layer that's in the new model is not the selected layer that we want to change, we'll do nothing. We're just adding the model what is originally in the old model, we'll add into the new model. And then with this, if it's the one that we want to be searched, it will do the same thing from the building blocks that we had before, the convolution 2D, the average pool, and as well as max pool. It would choose a random one of them, or choose nothing at all. That's the option too if we just want identity mutation. That would replace whatever layer that you have inside of your model, and then I will mutate it, and then obviously you add your prediction layers, you drop out layers, and then you return your new model. Basically, you return your child model at the very end of the function, and this is the actual aging algorithm. So initially, you have your population as empty, your history as empty, and you have your I as a placeholder for later on. Just give you try to use I as the key of your population. So you have an older population. When you want to remove it, you can remove the smallest number in that dictionary. So it's easier for you to just go using the number. Well, at least that's how I felt about it. And then while the population is smaller than 4, because I'm just testing it out in this code, I use 4 as my population. The model will random search. We will random search the model, and then we will evaluate that model, giving us the accuracy as well as the actual model. And then we will add those two into population. For here, the first round, so it will just be 1, and then add that into there. And then we also add that into our history. History will contain all the model from the beginning to the end. So that's the history model here. And then you do you do +1 of your I each iteration. And then you move on to your actual evolution. So here I'm doing 6 evolutions, so it's 4 + 6, that's 10. First, you do your sampling. So you have a random empty sample sets, and then your sample is, for me, I set as 3, just for easier computation. You have your list. That's the list of the population keys. That's basically giving you all the keys that's currently in your population. So you can then choose a random model in your population, and then add that model into your sample. And then the parent here is choosing the best performing model. So this will give you the best accuracy that in your sample, because remember that in all of our population, we've already added the model accuracy into it anyways, so you don't have to calculate again. All you need to do is just grab that from the population, and then basically having that max, you select the maximum one in your sample, and then that will be parent. And then parent, this actually gives the key for your parent, and then you use the key to get the actual model from your population, and then you get your child by using the mutation that we mentioned before to mutate and give your child model. And then obviously you train and evaluate your child model again, and then this would add your child model into the population, and then history would just be the history, and then you have I equal to I + 1, giving you when you iterate through this. And here is when you delete your key equal to minimum population key. This just grab the key for the oldest member in your population, and this code here will delete the oldest population. And after how many, for us is 10 iterations complete, this will give us the final model. The final model is the best performing model should be in our history, not population, my mistake. And that will return the final model. Obviously, this testing, this give you an idea. So initial search, for this here, initial search, you've got comp to the max pooling and flatten and dense. So that's the initial search, and then you need to search the second one. That's whatever it has here, and so on and so forth. And then from this point onwards, it started mutating, and you just mutating through however many you want. This is what I did here, and then after 10 search is done. 10 is the number of models in the history, and 4 is the number of in the population. And then I just printed the final model. And obviously it's not going to be good because you only have 2 layers, and you're only doing it for 4 evolutions. So it doesn't really make much difference. So I think you need to at least do 100 evolution to get some promising results.
And you can plot finally, like what's your final model look like?
Yeah, I can plot that. Yeah, but I haven't run it here. But yeah, I can plot that if you yeah. So yeah, that's the code for aging evolution. Obviously, I think there's might be some minor things like that that I haven't picked up when writing it. But if you see something when you're using it, let me know.
That's great. So any question, guys? So any question on this one, guys?
Not from my side, yeah.
Not at the moment.
Yeah.